Hi guys, I am Parampreet Singh and today is our fifth session on data processing in our machine learning playlist. So as we have done 4 sessions till now, and you can access all the recordings of my sessions in my YouTube channel. Um, so here you can access all the recordings, earlier 4 sessions. Okay, so till now we have done 4 sessions and today is our fifth session, which is on data pre-processing. So as earlier we have discussed, there are various steps in building a machine learning model from end to end. So uh, today we will be focusing on this fourth step, which is data pre-processing. So let's start. uh, in today's session, we will be mainly participating in this competition, Titanic Machine Learning from Disaster, and you can join this competition via this link slash competition slash Titanic in Kaggle, and you can click here for join the competition, and after that you will be able to see the data. So this is a playground competition based on the Titanic ship, and in this competition we have to predict whether a passenger has survived or not. So 0 for no and 1 for yes. So this is a binary classification problem which we are solving today, and we have various features in this. So as you can see, this is the train.csv, training data, on which we will be doing the complete training. So let's start. The first step is to import the data. So let's import the data first. Okay, let me reload it once. So yeah, here just you just have to create a new notebook via click on this create and new notebook. After that, what you can do is click on this arrow in bottom right corner and click on add input. Select competition datasets and just copy paste the title from the competition. Okay, and then you can in the filters click on hotness, so it will give you just the best uh, result, like the most accurate one. So this is the actual competition dataset, so we'll just click on this plus button and it will add the dataset, adding data source Titanic. So now you can see this is added in my dataset. Okay, in my notebook dataset. So it has three files: train.csv, test.csv, and this gender summation. This is a sample summation file. So let's start. The first step is to run this cell, which will show us the parts of data we have. So we will be mainly working on the training dataset. So let me copy this part. So these are all the steps. Let's start with the first step. So the first step is importing required libraries. So we will mainly using 6 libraries, but let me import one by one first. As upon the requirement, import pandas as pd, matplotlib.pyplot as unity, import cborn as sls. Okay, see, so these are 4 main libraries which we mainly use for data analysis stuff. After that we will import scikit-learn according to the usage. Okay, second step is loading data. So I have already copied this train.csv path. So what I will do is I'll just write train underscore df pd dot read csv and I'll paste this path as it is. Same I will do for test data, pd dot read csv, and I'll just replace the name from train to test. As you can see here, the path is same, only the file name is different. So I will run this cell. Now I have let's move on to the third step, which is EDA. We will not be doing EDA much in detail, we will just see the samples only. Okay, rough, little less EDA, because main topic is data pre-processing today. So let's check our training data. So this is how data looks like. So it has various columns. Okay, first let's copy the description of all the columns from here. So let me just paste it in here and is, yeah. So these are all the columns we have in embarked port is from where they have joined the ship basically. So there are three ports from there from the where passengers have uh, embarked, and then we have P class. P class is same as the berth we have in trains, um, like first AC, second AC, third AC, sleeper class, general, like this. So first upper, second middle, third lower. So these are the P class 1 2 3. Then we have age. Age is fractional, like for the smaller passengers, like whose age is less than 1, for basically newborn babies. Then we have SIBSP. So these two columns are family relation column. First column represents siblings or spouse. So this is 1 and 0. 1 is for siblings, 0 is for spouse. Similarly, we have second column, which is parent and child. So parent and child column is here. Okay. Then what we have, like here you can see passenger ID. Passenger ID column is like, as the name represents, it's the ID. So ID will be unique. So what we can do is we can treat this column as an index rather than a column. So I'll just write index call equals passenger ID, and I'll just copy paste as it is in my test data frame also. So I'll run this again, and let me run this again. So I have passenger ID here. Okay. So now let's look into the column data types. Okay. How can we will use info function. So here you can see we have two float columns. One is age, second is there. Then we have four integer columns, and then we have five object columns. Okay. So okay, now third thing, one more thing let's do, which is describe. So it will give us some description for our numeric columns, which are float and int. So this is for the survived. Of course we can ignore the survival one because this is a target label. Then we have P class, age, SIBSP, PRs, and fair. Okay. So like PRs, par ch, and so this is like minimum, maximum, and all these values. So like while doing EDA, okay, let's now move further first. So like this is a little bit EDA which we have done. Now let's move to our fourth step, which is data preprocessing. Okay. So I'll just write it here, data preprocessing. And in data preprocessing, what we mainly do is we handle the missing values. Okay, handling missing values. Second thing what we do is transforming columns. So we transform the columns mainly. How? Like we transform sometimes numerical columns also, and most of the time categorical columns. Okay. Also, like we do some other stuff also. For example, handling outliers. Okay. So what are outliers? So outliers in data is like um, which basically affect the distribution of the data. So in the area itself, if I like plot box plot, so okay, so let's first like plot a scatter plot. Okay, so trend here plot, and I will write kind equals scatter, and here I will pass x as age and y as, let's pass fair. Okay. So here if you see, uh, these are the main like the data distribution is like this generally in age to fair relation. But here you can see in age, like we have two outliers. Like in the 40 age, two persons have the fair which is more than 500, which is not like, which is an anomaly in the distribution, right? Similarly, here we have one outlier, here we have one outlier, like 60, for 60 there is only one passenger. Okay. So these are also like some of these outliers. Okay. So we mainly have to handle these outliers. How can we handle? There are various means. We will look into some of them. So there is, okay, let me show you one another plot also, which is box plot. So this is a box plot. This basically represents shows us the distribution mainly like the data. Also it shows us the outlier. Okay, so um, like here in age, okay, let me just increase the figure size first. Plt dot figure fig size is 10 comma 10. So now here if you see, this is the box. In a box plot we mainly have a box. This is a rectangular box where all the data mainly lies. So this lower line of the box is represent 25th percentile. This upper line represents 75th percentile. Okay, and this is the IQR range, interquartile range. Okay, from this line till this line. So all the data is mainly reside between this range only. And this green line which you can see in the middle, this is mostly the median. This is the median, so it represents the 50th percentile. Here the median is here like close to the 25th percentile. That means uh, most of the fairs are like around 25th to 58th percentile, and some are in 75th also. And apart from that, these circles which you can see, these are the outliers. Like, so these outliers which you can see from here, like these values which are not in the distribution and which basically affecting the distribution, like the range is increasing from here. Similarly here, like in fair we have a lot of outliers, like this you can see. So this outlier which is here, this is that outlier. Okay, so this is how like we basically analyze those outliers in EDA, and in data pre-processing we handle those outliers. Okay, so let's first start with the first one, which is handling missing values. Okay, so what we will do is, let's first write handling missing values. So there are various means of handling missing values. First is uh, like mainly we will do is imputation. Okay, we will impute some value. Like we will mainly replace the missing value with some computed value or some different value, and we call this process in machine learning as imputation. Okay, so but in imputation what we do is, like we either impute the mean to the missing value, or median, or mode. Okay, or we can impute like a constant value, or we can there is also an okay, we can also impute like some custom value. Okay, and there is another way which is called KNN imputer. uh, KNN, which is mainly KNN imputer, which mainly represents k nearest neighbors. So it uses Euclidean distance and find whichever neighbor is um, nearest. So it will impute that value to the missing value. Okay, nearest neighbors. So yeah. Okay. Now let's start with one by one. So okay, let me give you one example first. Um, okay. So whenever we let's suppose, okay, here we have various columns, right? If you see, we have p class, survive, names, x, age, and all. So okay, let's first see where we have the missing values. First we should check that. So what I'll do is train df dot is na or is null dot sum. So it will show me the columns which have missing values. So age, cabin, and embark. So let's take the age column once. Okay, so let's suppose we have age column, um, where the data is something like, if I have this in my age column. Okay, so the data is something like, let's say 15, 10, 20, nan. So nan basically represents missing value. Okay, and we have, let's say 30 here. So these are okay. Let me take one more also for just a sample. Okay. So these are the a sample of the age column. So there are various means as I told. So first one is mean. So mean we mainly represent via x bar. Okay. So how mean is imputed there? So it basically first calculate the mean. So if we see, we have mainly 5 values, non values 5, and we calculate sum of observation upon number of observation, where it is 30, 30, 60, 70 and 85. So it is 85 divided by 5, which is approximately up to 70. So yeah, so this is 17. So this is the mean. So what imputing the mean value is we are replacing the nan values with the mean of the data set. Okay. Then we have median. So median is of course obviously imputing the middle value. So if we sort our data set something 10, 10, 15, 20, 30. So here we have 5 values, and median of for odd number of samples is n by 2. So here n is 5, so basically 2.5, so this will be considered. Okay. So this is the median, and this value is imputed in the nan value. So this is the median approach. Then we have the mode. Mode is basically finding the most frequent value, like which value occurs most. So 10, here you can see 10 occurs twice, rest of them occurs only once. So 10 is the mode. So imputing mode means imputing the 10 here for in this example. And these are the three main techniques, and we have a constant also. So let's suppose I have defined a constant, let's say x equals 25. So my 25 value will be imputed in place of nan. Okay. So this is a constant approach. These are some of the main approaches we have seen. Then there is a custom value. Custom value, you can say custom function. Okay. So how custom function? Let's suppose here we have a sex column also, right? So in sex column we have male and female. So let's say I have defined some function, def average age. Okay. uh, where I am finding the average of male and average of female. So and I am checking if the nan if the sample where age is nan, I am checking whether the sample is of male or female. If it is male, then I am replacing it with the average of male age values. Similarly for female, so I can create any custom function also, and I can impute that value also. Then there is one important or you can say one interesting way, which is KNN. So KNN basically works on the k nearest neighbors way. Okay. It works similarly. So it first mainly uses uh, like some other columns also, some other numeric columns also, and it finds their Euclidean distance. Whichever distance is the closest, it uses their value. So let's suppose okay, there is a fair column also, right? So let's say this is the fair column, this is the age column, and let's suppose okay, what numerical columns do we have? So there is a P class column also. So this is a P class. So let's say age is like this, and fair is like this: 20, 50, 100, 60, and nan here, and here we have 1, 2, 3, 5, 20. So k nearest neighbor, what it does is it takes some n sorry, k K basically represents how many nearest neighbors should we consider. So let's suppose if it is 1, then it will take the nearest neighbor, like the one nearest neighbor for this, like nan for these this and this, and it will compute the Euclidean distance from this sample to this and this sample to this, whichever has the lowest Euclidean distance. Let's suppose this sample has the less Euclidean distance compared to this, so it will impute 10 here. Okay, so this is how k nearest neighbors works, imputation works. Okay, so this is how we mainly do the imputation. Okay, so now let's start doing the imputation. Okay, uh, before doing the imputation, there is an important step, which is like splitting our data set. So generally, like what we have is, let's suppose I am just im- imagining that we have a data set something like this. Okay, so these are all the samples we have, we can say. Okay, so what we mainly have is, like, here we are participating in a competition, so we have a separate data set which is a test data, right? So this is a test data and this whole is a training data. So we have this training and test data, right? But generally, like when we deploy our machine learning model in production, so we don't have any kind of test data. We mainly, like, here we can validate our test data from the leaderboard score, right, from the accuracy which we are getting in the test data. So like here we have some kind of validation, but in production we don't have any kind of validation. We just have to predict directly until and unless we are gathering the feedback from the user, right? uh, so like what we generally do is, like, to evaluate our model, like how our model is performing. Here we can evaluate via test data and score in the leaderboard, but generally we can't, right? So what we do is, we split our training data into two sets. First one is training, which mainly goes for the training the data, training the model. Then we have validation data set. Validation is also known as dev data set. Okay, development data set. So both are like interchangeable names. uh, and we mainly train our model, like we call the fit function on this, and then we call the predict function on this data set, and we evaluate our model based on this validation data set. So then after that, whenever, like, it reaches some baseline performance, so let's suppose baseline performance is 80% accuracy. Okay, so if in our validation data set, after predicting, we are getting 80% accuracy or more, then we can proceed further and deploy our model, or like share our model to whomsoever we have to. If it not, then we can improve our data. We can use different techniques in machine learning to improve our score, right? Then like, generally, while splitting this data set, we mainly split our data set into, like, in various ratios. Like generally we use this ratio of 70 is to 30. So 70% and 30%, like, from the complete training data set, we can split our 70% data set into training and 30% into validation data set. So this is 7 is to 3 ratio normally, and uh, like, there are other ratios also, like some people do in 60 to 40, or some do 80 to 20, or 70 to 30. So Generally we do this. And if we are like, if we don't have any kind of test data already, so we split our data into three parts. So we can do something like this, 80, 15, 5, or like 70, 20, 10. Okay, this is the training, this is validation, and this is test data. So this is how we can do the splitting. So this splitting is important for model evaluation. So first we will do the splitting, then we will do the imputation, basically data pre-processing. So this is the first step which we do in the data pre-processing. So let's do the splitting of our data. So for splitting we need like a function. So we will use from sklearn we will use a model selection like API, in which we have a function named train test split. Okay, so we will be using this function which will help us split the data into different sets. So we already have a test data set here, so we don't need three sets. So we only need two sets, which is one is training and another one is testing validation. So let's do it. So let me just before that, let me simply okay, so let me simply write here data splitting. Okay, so it is splitting data into training and validation set. So let's do this. So generally, okay, before doing that, we have to like differentiate our target also. Okay, target and the feature. So let's do this one. Train df dot drop columns equals survive. So this is our feature label survive, and let's take this in y value. So now we have like our data in x to y. Okay, in x we have all the features, in y we have all the target labels. So now let's do the data splitting. In data splitting, what we do is like, let's use the train test split function. In train test split, we first have to pass the features, and then we have to pass a target label, and then there are like two ways to pass the ratio. What we can do is we can either pass a training size, let's suppose 0.8 here. It represents 80% of the data will be uh, for the like 80% of the data will be distributed for the training set, and rest 20% will be for the testing set. Okay, or we can pass test size parameter 0.2. So it both of these parameter represents the same thing, and the ratio should be of course 1. So we can generally we use test size. And here we have another parameter which is called random state. I will tell you about this a little bit later. So if I normally run this, I'll get these 4 columns, basically array, like which has 4 data frames mainly. uh, like first we have uh, uh, what the 4 things it returns. First it returns is our training data set. Okay, then it returns the validation data set for the features. So I am representing our training features as an x string, and our validation in x valid I am adding all the validation features. So then we have our y labels. So I am writing y train for all the target labels which are being used in training, and then y valid which will be using for the validation of the model. Okay, then if I run it, so now if I look into my xtrain dot head, here you can see I have got these uh, values. Okay, so now if I, let's suppose, let me do extract. Okay, not extract shape, xtrain dot shape. So this is my data set. It has 712 columns. In my training data is 10 columns, 712 rows and 10 columns. So let's say, okay, before that, here if we see this is my x dot shape, right? And similarly, like for the validation, here it is. So 80% of 891 is approx 712, and rest is in the validation dataset. So similarly, same for the y also. Okay, if I do y train dot head, so these are my y train, and if I do y train dot shape, here this is the shape. Okay, so now there is one question arises, like will the distribution be same while splitting the data set? So yes, the train test split function of scikit-learn library will handle this for us. So it splits the data set completely in equal distribution for all the features. So let's take this which column. Okay, let's take this embarked column, and let's see in the x embarked what is the ratio we have for all different values. So I'll set normalize equals to, here you can see for s we have 72%, and for c we have 0.18, and then for q almost 0.1. Okay, so this is the ratio. Now same I will do for my training set. Now here if I write x train, and here if you see I have like the same ratio here, 0.72 for the s and 0.18, and similarly for this. If I check for my validation set also, x valid, there the distribution is same. Okay, so it handles our distribution. Now there comes a point like this parameter random state. It basically it gives us the same data set if we set the random state to some constant value. So if I like, doesn't matter how many times I'll run, I'll get the same data in my training and validation. So it helps us in like while doing the model training. If I don't set any random state value, it will give me every time, it will give me separate like different data. Here you can see the distribution will be same, but the data, the samples will be shuffled. Okay, so here you can see, so that's why I said we can set a random state value to any integer, any like 32 bytes integer. Okay, bits, not bytes. So this is my data set. Now I have did the like splitting. Now let's go to the handling missing values. So as I said, like we can handle missing values by various means. So let's first try with the mean. Now for doing all this, we have a function in our scikit-learn library. Basically we will mainly use um, the API of sklearn, which is impute. Okay, in this we will mainly use we have two functions, two classes. One is simple imputer. Okay, another we have is knn imputer. So these two classes which we will use today. Now um, as an intro, just knn is for the knn one, and rest for the rest we have simple imputer. So let me just define my imputer here. So it is simple imputer, and in the simple imputer we have, if I run the question mark with the simple imputer, here you can see this is the signature. We have a strategy parameter which basically tells us by which strategy we have to impute the null values. So we can either do with the mean, here if you see, we can either do with the mean, median, most frequent. So most frequent is the mode. Okay, mode is the most frequent, of course. Then we have a constant. Okay, um, now if I let me remove it. So by default strategy is mean. I'm just explicitly writing it for the sake of confirmation. Then in imputer, like in the simple imputer, we have three functions. What are they? Okay, so let's go here. First one, like in our mainly in data pre-processing in all the classes of scikit-learn library, we have these three common functions. Okay, so one is fit, then one, this is 2, and here 3. Second is fit, okay, yeah, let me write transform. Second is transform. Third we have is fit underscore transform. Okay, so what all these functions are? First one, the fit is basically it compute the values, okay, based on the strategy we have provided. Transform is what it replace those, it replace the values with the computed value. Then we have the fit and transform, it do both of the things. It first compute and then it replaces. Okay, so compute and replace, it do both of the things together. Now, like when to use which one, let's check this. So like mainly all our model training will be based on the training data, right? So what we will do is, we fit our data into, like we fit the imputer on our training data. Okay, then of course we have to transform our training data also, like we have to impute the missing values in our training data, so we can call transform here. Okay, and then we call the transform in validation set, and then we call the transformation on test set. Why not fit on validation and test? Let's suppose, like mainly we have to do all the model training based on the training data, so that's why we fit the, we compute the values based on the training data only. And also, here like we have a lot of samples in validation and test, but let's suppose we have only one sample, so how will we compute some values, let's say mean, median or mode, and those one samples have null values, so how will we do that? So that's why we first mainly fit the data on training set, and we compute the value based on the training data set, and then we transform it. So like on train we are calling two functions together, right? So instead of calling 1 and 3, we can directly 1 and 2, we can directly call the third function together. Okay, and on rest of these two we can call the second one. So first we will call this on training, then we will call these two on our validation and test set. Okay, so this is the same for all the pre-processing stuff in machine learning, mainly in scikit-learn library. So let's do this now. As I said, we have a fit. Okay, so before doing that, let's take the nan values. Okay, nan column. Currently I'm just taking this age column only, because it is an integer, so we can work on all these three strategies, right? So what I'll do is I'll just write age here, and these are my like kind of nan columns. Now I will do imputer dot fit, and here I will pass my training data and only the nan columns, only the training data with only nan columns. Okay, so if I run it, here you can see it gives me the simple imputer, and it basically compute all the values. Now if I run transform on it, okay, before doing that let's check our data. Okay, so here you can see we have second value as nan and we have fourth value as nan. Now let's run this transform. Here you can see we got in second value we got this mean value here, right? So this is how um, this is how imputation works, simple imputer works. So yeah, as I said, like we can do the fit and transform together, and we can confirm whether it is a mean or not, like from here also, like here we did the describe function, and here we can see for the age we have mean this 29.699, so this is approximately same value up to 2 decimal places. Okay, that was for the that that was for complete data set. We can also like check for this uh, let's say dot describe here. So here mean is 29.33 and the same value is imputed here. Okay, so this is how we can do the imputation for the mean, and rather than using fit and transform I can directly use the transform. I'll show you this in second example. Now instead of using the mean only, let's do with a median. So I'll just rewrite this with the mean imputer. Okay, now let's do with the median imputer, where we just have to change the strategy from mean to median. Now if I run it, you can see it fits the data and with the strategy median. I can directly call transform here. Okay, here you can see the middle value is imputed. This middle value is 28. How we can verify? uh, Here like, okay, here if you see the 50th percentile is the middle value, which is the median, it is 28. Also like let's check the mode value also. So with the mode function we can check the mode is 24, so we will check that also. So let me just toggle the output. Yeah. So similarly we can do for the mode also. So if I just replace it, mode imputer and strategies mode, if I run this, okay, there is no strategy called mode, there is strategy called most frequent. Okay, yeah, so this works. Here you can see the mode is 24, so it is imputed here. And we have one more fourth strategy, which is a constant value, right? So I'll just write const. Okay, and for the strategy, I guess let's check the name once again. So in the strategy we have constant. Okay, I have to set up constant and I have to fill the fill value function also. So I can set constant here, and in the fill value parameter let me set, let's suppose 25. So each value will be each null value will be replaced with 25. Okay, these are like the four ways of handling missing values out of 6. The fifth one, custom function, we can define any custom function and we can just apply with it. Okay, or using apply or using map. Okay, we can do that. And then we have the knn also. Before doing the knn one, let me like do, okay, so these are the like four ways of doing the imputation. Let's suppose we are going with the mean strategy on. Okay, so there is one question arises while doing the imputation, which one should we follow? Okay, mean, median or mode. So that of course we can't say right now. Let's suppose we did the mean strategy on all the non values right now, and we created our model and we did the evaluation on validation data set, and we got some accuracy around 70%. Okay, then we have to like we got the accuracy using mean, we got the accuracy around 70%. Okay, and let's suppose our baseline was 80. Okay, so what we will do is we will change the strategy from mean to median, then we will try again. Here let's suppose if we got 75 now, so now I will try mode, and here let's suppose I got 84, so mode is working for me, then we will use mode. So it's just trial and error we can do. We can also look into the distribution after imputation. Of course it will help, it can help, but it will not always help. Okay, so yeah, now let's suppose let's choose the mean imputer only. Okay, so normally uh, okay, let me write the transform here. Normally what it does is it gives me a array. Okay, an nd array, not the like the data frame which I was passing. If I check here, like let me copy it from here, If we check here, we have a data frame with the age column and all the values here with the index. So what I'll do is I'll simply convert this to a data frame. Okay, I'll just write pd. Okay, let me create a new line, pd dot data frame, and I'll put all this into this one. Okay, now it will give me a data frame. Here, like you can see, in the data frame, like we have custom indexes also, right? This passenger ID. So how can I get that back? I'll simply write index equals, I'm using the training data, so I'll just use the index of training data. Okay, now if I run it, here you can see I got my index back. Now the one thing left, which is the name of the column. I can get it by, there are like three ways. I'll discuss all three ways in three sets. Okay, first one is like simply passing nan calls, which is like the columns which I was selecting. Okay, let me toggle the word wrap. Yeah, so here you can see this is like the columns I have passed. Now if I run it, here I get the data set back in the original form. So this is how like we do this stuff. And also like okay, now just this thing, now same thing I can do for the test data and the validation data set also. Okay, so I'll let me write comment here. This is like the imputation with mean value, and then we are fitting and transforming mean to training data set, and then transforming validation set, and then transforming test data set. Okay, so currently I have just copied these columns as it is. So for the validation I have xvalid, right? So I'll just replace the data frame only. The columns will remain same and the indexes will also be different because the data set is different. Now for the test, the columns will remain same because I am doing the imputation on same columns. Rest all the things remain same. And now I have to like assign the imputed data frame, okay, to the original one. So I'll just copy this one which I have passed here to the front and I'll assign it here. Okay, same thing I'll do in validation, and same thing I will do in the test GF also. So this is how we do the imputation. Okay, now as I said, there are three ways of like assigning the columns. First one is nan. If like we have only one column, we can simply assign like this. Okay, this is the first way, this is the second way. Now third way is like if we check our main imputer, okay, this is, yeah, now if we check our main imputer, we have a option name which is feature names in. This basically specifies what are the feature names we have passed. Okay, we can also assign this one. If I write columns equals this, all three will work. Okay, now if I check my extrain of num calls, here not the num call, sorry, nan calls, here you can see all these values will, all the non values will be imputed with the mean value. Same for the validation also, x valid. Okay, so and same for the test data set also. So this is how imputation works. Okay, now what we like, okay, so this is like we have done for the imputation, and I hope you all are now clear with all these ways except the KNN one. Okay, the KNN one I will explain it to you later when we do some feature transformation also. Okay, now like we have three columns mainly which are like, which is having null values, but let's first like we only did for the age column right now. Let's first convert other categorical columns into like numerical features, because machine learning will only work in numerical only on numerical data, right? It cannot interpret any categorical, any string kind of values. So uh, okay, let me write here handling, let's say transforming categorical data. So in transforming categorical data, what we mainly do is we use encoders. Okay, so what are encoders? Okay, encoders basically uh, encode the feature. Okay, I'm just saying it literally. It basically map the values in the features to like some certain integer values. Okay, it which is mainly encoding them. Okay, to some different type. So there are like various kinds of encoders we have in scikit-learn. Mainly we will be using three today. First is ordinal encoder. Okay, second we have OneHotEncoder. Third we have label encoder. Okay, so these are the three encoders we have. Now in ordinal encoder, um, like okay, before going into that, let's first get all the categorical columns. So I'll just write cat columns, and here I'll write extreme dot select d types, and I'll just include only object columns. Okay, and I'll write dot columns, which will give me all the categorical columns. If I run it, you can see I'll get all the categorical columns here. Rest are all the numerical columns. Now these are all the three encoders we have. Now let's see what these encoders are. Okay, but before that, let's see some values we have in different columns. So in column name 6 we have these two different values, and now let's check for the embarked. In embarked we have three, in 6 we have two different values, in embarked we have three different values, and in let's check for the cabin. In cabin we have 162 different values. Okay, so okay, now let's get into the encoders. So let's suppose um, okay, let's check right now, let's just check that embarked column. Okay, this is the embarked column we have. I'm just writing some sample data from it. So in embarked we have values like S, C and Q, right? So I'll simply write S, C, Q, Q, C, and so on and so forth, right? So of course this is just a sample. Now what ordinal encoder do is, here if I write ordinal, so what ordinal encoder do is, ordinal encoder basically map all these values to some certain integers. So S will be mapped to, let's suppose 0, let's say 0, and C to 1, Q to 2. So it will map all the k unique values we have in the feature. Okay, uh, so it mapped them to some integers, then it basically gives me the transform data set. So now my data set will be 0, 1, 2, 2, 1, and so on and so forth. Okay, so this is how ordinal encoder works. Okay, now let's check how one hot encoder works. Let me write one hot encoder. So one hot encoder, as the name suggests, it's one hot. How, like, okay, let's check this. One hot encoder, what it do is, it creates all the like k columns. Okay, k unique columns, like based on the k unique values, it create k unique columns. Okay, how, like here we have three unique values, right, in our embarked. So it will create three unique columns in basically a new data set, you can say. It will create three new column data set. The first one is I'm simply writing E for embarked, E underscore S, okay, then E underscore C, then E underscore Q. So this is what one hot encoding do. And let me just yeah, increase the size. Okay, so what it do is it checks if the first one is S. So here the first one is S, so it will mark 1 here, and for the rest of the columns it will mark 0. Okay, so these are all the zeros. And now for the second one it will check this is the C, so for S it will mark 0, for C it will mark 1. And now for the Q, 0 0 1, and again for the Q, 0 0 1. And now here it is C, so it is 0 1 and 0. Now same it will repeat for all the samples. So this is how one hot encoder works. Okay, now this is how these two encoder works. Now there comes a label encoder. Okay, label encoder is same as ordinal encoder, but the only difference is ordinal encoder works on multiple features at once. Okay, let's suppose we have to encode embarked, cabin, name, all these columns together, then we can use ordinal encoder. But if we are if we are using label encoder, then we have to create three separate encoders for three different categorical columns, like one separate encoder for embarked, one separate encoder for uh, like um, one column, let me write, yeah, one separate column for embarked, one separate column for 6, one separate column for name, and one for cabin. Okay, now like here you can see ordinal does not change the shape of our data set. Okay, the shape remains same, it only transforms the values. But one hot encoder change the shapes also, so it create new columns. So like while choosing which one encoder we should use, generally what we do is we set some threshold. Okay, threshold for like what, uh, let's say uh, in all the, like here we have these categorical columns. Okay, so in all the categorical columns we can set if there are less than or equal to 5 unique values, then we will use one hot encoder. If there are more than 5, then we will use ordinal encoder. Because let's suppose like here in cabin column we have 126 unique values. So if we use one hot encoder, it will create 126 columns, extra columns. Okay, but ordinal encoder does not create any extra column, it just transform it. So yeah, it is up to us, like we can set some threshold value. And of course, like sometimes ordinal encoders, it is like same as the imputation. Sometimes ordinal encoders gives us better accuracy, or sometimes one hot encoder gives us better accuracy. Okay, so at the end it depends upon the evaluation, like model evaluation, which one is performing how. Okay, so we have talked about all these three encoders. So now let's start. Before starting, let me set some threshold. So let's say threshold equals 5 here. Okay, now what I'll do is I'll create one list, like a list you can say, in which I'll choose only those columns which are having unique values less than this threshold, or less than or equal to this threshold. So I'll do for I in cat calls. Cat calls is a list of columns, categorical columns, right? So for I in cat calls, if len of x train of I, remember we have to do everything on training, we have to do main pre-processing, fitting the data on training only. X train I unique, so it will give me all the unique values, then I am computing the length of it. Okay, if length of this is less than equal to this threshold, then add it to the OH calls. Okay, what OH represents, it represents ordinal one hot encoding. Okay, so these two columns I'll use for the one hot encoding. Now let's create for the ordinal also. So odd calls, there are two ways to do this. I can like simply first copy this and I can write greater than threshold, right? One way is this, and the other way is like replacing the if condition with this: if I not in OH calls. So either the column will be in OH or either the column will be in ORD. Okay, so first we have to select those columns. Now after selecting for the ordinal encoder, okay, let me write ordinal encoding. Ordinal encoding. Now let's create our ordinal encoder, which is just simply by writing ordinal encoder. Now it also has the same functions, which are fit transform and transform. So I'll just directly use the fit transform one. Okay, ordinal encoder, and here I'll call the fit transform function, and in that I'll pass the ORD calls, only this data set. Okay, now if I run it, okay, I am getting, okay, sorry, I have to import it first. I have done the import statement here. Okay, I forgot to cite. So now let's first import it from sklearn dot preprocessing library has these encoders API. So let's okay, import this one by one: ordinal encoder, then one hot encoder, then we have label encoder. We have also other encoders as well. We're just mainly looking into 3 encoders as of now. Now what we do is, yeah, so let's run this again. Here you can see this is now transforming all the ordinal encoders into these values. Of course I'll getting the NaN values here also. Okay, so don't worry about this. Now here also I'm getting the same matrix, not the data frame. If I check the data here, this is a data frame, right? So again I can do the same stuff. Let me copy it to another cell. Okay, yeah, so what I'll do is I'll first create a data frame of it, pg.data frame. Now you can see I got the data frame back. Okay, of course ordinal encoder does not create any new columns, so we don't need to worry about the columns. Now we have to set the index. So by default index is this. Let's set up our index also. Index equals, I'm using the training data here, so extend.index. You can see index is here. Now I have to set the columns. Okay, I'll just pass columns equals, there are again 3 ways. So like, let's first use the basic way only, which is ORD calls. Okay, let me the word rep. Yeah, now here you can see I got the data in my original format. Okay, but now it is encoded, ordinal encoded. Now these values are transformed. These are by default float, but there is no any float value. Okay, all these are integers only. We can of course transform it into using as type function and write np.int, let's suppose 32. Okay, you can transform that into integer columns only. So it is giving me invalid value encountered. Okay, I can write np.64. Okay, yeah, got it. Not here, I have to do it here as type np.int 32. Okay, in casting error, cannot convert. Okay, so there are null values also. Okay, so I have to figure that also. Don't worry. Yeah, because of that null, for the non values, because nan comes under float. Okay, so that's why it is giving the float. In the float, by default it gives us in the float. Okay, now there is one thing. Let's suppose while distributing all this, um, let's suppose some okay, we have different names, right? So let's see. Okay, yeah, let's say in the name column, this is my name column. Okay, in my name column I have different names, A, B, C, D, and so I'm just writing some sample. So this I have split it into two types data sets, right? So first one is train and second is valid, and we also have another set which is test. Okay, so let's say in train we have names only A, B. Okay, but in okay, A, B and C, let's suppose we don't have any D, but in validation we have D, and in test we have some new names which are E and F. But in our ordinal encoder, and we have fitted the data based on the training data, right? So how it will handle D, E and F? Of course we cannot do the fit here, because this is the validation, this is for validation, the validating the model and testing the model. Okay, so how to handle these unknown values? So these are unknown values, right? So how to handle these unknown values? There are like two parameters we can pass. First is handle unknown. Okay, in handle unknown, by default it gives us an error. So what I can write is, I can write use encoded value. So it will just ignore the unknown values, first one. Okay, first of all, then we have another parameter. Okay, I forgot, I guess, which is unknown value. Yeah, so it will, what it does is, of course it has to replace that, transform that into some value, right? So what I'll do is I'll transform all the unknown values with -1. Okay, I'm taking -1 here. You can take any value, or you can take in fact any series of functions or something like that. It's up to you. Okay, so now if I run it, of course for the training it works fine, but for the validation it may cause error. Now the same thing I will do for the validation and for the test also. Okay, so let me write the comment here also. So creating ordinal encoder, fitting and transforming training data, transforming validation set, then transforming test set. Okay, now let me like change these values also, because we are using validation set, and here test df. Okay, now I told you there are various ways for columns. The first one is this, of course. The second one is passing the direct list. Okay, this list also we can pass. If I just copy it directly, it will also work, because the column names remain same. And here like for this, okay, there is also third way which I'll show you here. So in the ordinal encoder also we have one parameter called feature names in. Okay, it gives us all the feature names in. Also, like similar to this, we have an function name get feature names out, which will give all the feature names. These will remain same, because we are not creating any new feature or changing any feature, right? So I can use those two like parameters, or like either that parameter feature names in, or either this function. So now, okay, also I have to assign it to this, so I'll just copy paste it here because I'm encoding them. Okay, and for the test CF also. Now if I run it, of course I won't get any output. Now let's say, okay, yeah. Now here what we will do is, okay, let's check our training data now. Strain.head, here you can see these are all transformed. Now we are left with two columns which are sex and embarked. We will handle them with the one hot encoding. Okay, now these are transformed into numerical values, right? Now let's go for one hot encoding. I hope this is all is pretty much clear to you all. If not, then you can rewind the video, okay, and watch it again. Now let's do the one hot encoding. Okay, I have selected few columns which are in OH calls, right? So these are two columns on which we have to do one hot encoding. So let's create our one hot encoder. I'm just writing a shorthand here, one hot encoder, and here, like, okay, now if I just simply create this one hot encoder, OH encoder, similar to the ordinal encoder, it has three functions. First one is fit, second is transform, then fit transform. All work same way. I'm just directly using fit transform. Now I'll pass extrain OH calls. Now here you can see I get this kind of output. So in one hot encoder we have like some additional parameters which we have to pass. Okay, so first one which we pass is okay, so let's check. Yeah. Okay, so by default it is returning us a sparse matrix. Okay, but we need to see the values. How can we get the value? Of course we can, this is a compressed, you can say, format. We can iterate from to it, but we don't need to do so. We can directly do it. How can we do so? We can use sparse underscore output to true. Okay, okay, I guess, yeah, false. Now if I run it, you can see all these columns are transformed. How, like, now you will wonder which one is which column. Okay, like, okay, let me just, yeah, remove this one. So here I have these two, so the columns will be transformed in the same order only. Like how for the sex column we have two values, male and female, right? So for all the female, it gives the female value to 1. So these first two columns represents the sex column. Okay, then these three columns represent the embarked column. In embarked we have 3 unique values, so these are 3. Okay, now of course, now this is also giving me an array, an ND array. I want the data frame back. How I will get it? I'll just simply write pd.data frame. I get these values. Okay, of course there can be nan values, so we cannot right now transform them. Now what we do is, okay, let's now go step by step. So first let's set up the index again, okay, which is extreme.index. So we have set it up the index. Let me set the word wrap. Yeah. Now for the columns, how do we specify columns here? Because in earlier, in ordinal encoder, it is not creating any kind of new column, right? It is just transforming those columns. But in one hot encoding, we are getting, instead of this one column, we are getting 2 columns, and instead of this one column embarked, we are getting 3 new columns. How can we name them? Of course we need a naming, right? As we will get confused in the 0, 1, 2, 3, 4 on these random names, right? Default names we can say. So for the columns, if we like check our encoder in OH-encoder, similar to the other encoders and computers, we have like these parameters. First one is feature name sim. Of course we don't need this because it only has 2 columns. Right now we get 5 columns, so we need some feature names which are of 5 columns, right? So how can we get those? I'll simply use this one, get feature names out, the same function which I have used here. Here the features are same, right? If I simply copy it and write feature names in, so both giving me same, but here if I do this like feature names in, and this is an attribute, okay, underscore, this is an attribute and this is a function. These are the features which we have passed, okay, but we are getting 5 features, we are not getting 2 features. What we will do is I'll run this. Here now you can see I get the first feature name as sex female, then sex underscore male, then embarked C, then embarked Q, then embarked S. Similar to this where here E underscore S, E underscore C underscore Q. Similar to this we are getting these. So these are all the 5 features, and here 5 features we have, right? 5 column names. So I can use this one for the column names. I'll simply write columns equals to this, and now let me set the word wrap again. So now if I run it, you can see I got my columns back. Okay, so now I can identify which one is representing which column, right? This is the prefix. Of course we can change the prefix also, but right now we don't need to. Now similar to the ordinal encoder, we may get some unknown values also, right? So we can use this parameter here, handle unknown. If we check the value, so there are like 3 values. In ordinal encoder we only have 2 values, either error or use encoded value. Here we have like ignore or infrequent if exists. So it basically do is okay, infrequent category, and so it basically map to the last position. So rather than this, what we can do is we can simply ignore those values. By ignoring doesn't means like it gives us the metric, like the values in object. No, it will give zeros to all those, okay, all the values. So now what I'll do is I'll simply pass a handle unknown equals ignore, okay, not encode, ignore. So now I got my data back. Okay, just to for the clarification, let me write the sample one here. Okay, yeah, now I got my data back. Okay, now I'll do the same thing for others also. This is for the training set only. I'll do the same for my validation set and same for my test set. Okay, so I'll write ordinal encoder here, and here I will write and fitting and transforming training set. Here transforming my validation set, okay, not test, validation set, and here transforming test set. Now I'll just simply replace this data set. So here it is just GF, and here it is just GF again. Now I'll assign this to the same. Okay, now here comes one new thing, which is okay, I can't assign it to the same columns, right? Because we have 2 columns here and we are getting 5 columns as of now. So what I can do is I can create new columns. How? I'll simply use this one, or I can just write out columns one. Okay, instead of writing out columns, what I can do is okay, let's create a new data frame once. Okay, so x xoh x train oh. Okay, similarly I'll do for the validation also. So here instead of train I'll write this, and here I'll write test oh. So now I got these. Okay, now let me run let me check this one first. Yeah, here um here if I like check this is my data frame, and okay, let me do only head here once. This is my new data frame and this is my original data frame. Now I want to add these 5 columns in my this data frame. There are 2 ways. Okay, I'll just show you just one way for the sake of like doing fast only. Okay, there are multiple ways, well, not only 2 ways in pandas. Yeah, so one way is um, what we do is okay, we can write explain dot join, and here I'll pass explain oh. It will give me the new data frame. This is now the new data frame, but here one thing is still pending, which is we have transformed the 6 column as well as the embarked column, right? Now I don't need these 2 columns, 6 and embarked. I have to remove these columns also, right? So I'll write drop columns equals oh calls, because oh calls are same. Oh calls are these, right? 6 and embarked. So I can do this. Now I get all in the data set I have. These are all the numerical features only. There is no object, okay, feature. Now I can just simply assign it to the training set, and same I will do for the test and validation. So I'll write x valid, and this is the test here. Okay, and here I had valid one, right? Here I had test oh, if I am not wrong. Yeah, test oh. So in ordinal one hot encoding we have to do this one another step. Okay, we have to drop the earlier columns, and we have to create add join the new data set with the new columns. Okay, that joining part we can do in multiple ways, of course. Now if I run it, okay, let me simply set it here also. Don't worry, here right now it is giving the output. Okay, this is just for the sake to see. Okay, now if I check my data frame, this is my new data frame. This is completely of object numerical values, sorry, not object. I can check also info. You can see all are intent float. There is no column of object data type, right? Now we have intent float. Now we also have null values, right? We can again do the same thing. Okay, now let's first check the null values. Where we have null values. In age we have already done, so we don't have. In cabin we have null values. Okay, and let's check the validation set also, because in validation it might contain any null value, right? So validation also have this, and okay, yeah, validation. What validation did is it created a new column named nan, which was done because of this handle unknown ignore. Okay, so those are the nan values mainly. Okay, don't worry, we can get rid of that also, but right now I'm not doing that. I'm just like simply showing you what this is mainly the pre-processing step. So for the cabin we have now, right? How okay, let's check in the test dataset also. Okay, now yeah, we have to drop that of course, because we cannot have any extra. Yeah, so we have same number of features. Okay, in test data frame we have a nan value in fair. You can say this is something new, right? Not in name, we have in fair. Okay, so we have to encode that also. So let's create a new encoder. Okay, now let me write it here. Imputing missing values. Let's create a new column. First let me write nan calls, which basically is this. If I simply do this, exchange is null sum dot index. These are all the columns we have. And how can I get the nan columns? There are various means to get the nan columns mainly. Okay, so dot index, with the help of dot index I can get this. Now for the nan columns, yeah. What I'll do is, okay, let me assign it to some variable. Let's say nan count. Okay, so these are all the values we have. Okay, let me set it here. Yeah, nan count. Now what I will do is I'll simply create a filter nan count where nan count is greater than 0. So it will give me all the columns which are having null values. Now I'll just write index here to get the nan columns, and I can simply do this nan calls and nan calls. Okay, now let's create a new filter. Let's say now let's use the mode, okay, instead of media. So mode imputer, which is simple imputer, and here strategy is most frequent. Okay, for the mode it was most frequent. Mode imputer dot fit underscore transform. Here I'll pass x train nan calls. Okay, now here you can see these are all the values I got. Of course I need to transform it to a data frame. Data frame index equals x train dot index. Okay, so instead of just passing the nan columns, I can directly pass the complete one also, right? Because we have some nan values in fair, we have, right? So we can handle that also. So for that what we will do is, okay, yeah, so yeah. Now if I like simply run this, I'll get all the data frame back. I can check here also, is there any null value? Okay, there is no null value as of now. If I check, okay, right now there is no null value. So now the same thing let me do for the, instead of fit transform I'll just do the transform. Okay, here I hit the fit transform. I should not do that. I should do this. Okay, I did a little mistake here. I just copied the fit transform. Let me recreate the data set once. Okay, here also it was this. Oh my god, I did a lot of mistake. Yeah, no worries. Okay, this is my transform dataset. Now I have selected the categorical columns. Now ordinal encoder fit transform. Yeah, okay, so here I got some okay, your func is not supported and the inputs could not be safely recorded. Okay, so how can I handle some NaN values in the ordinal encoder? Okay, so let's check here in ordinal encoder. So encoded missing value with NaN. So there is an option called encoded missing value equals NaN. So let's check this. So encode values of missing category is set to np.m and the data type parameter must be a float type. Okay, so inform NaN is not supported for the input types and inputs cannot be safely supported. Okay, yeah, what we'll do is yes, similar to the that ordinal one hot encoder, we can write encoded missing value with -1. If I run this, now it will run, it has run successfully, right? So now if we check our training data set, this is how this is. Now for the ordinal one hot encoder also we'll use the transform, not the fit transform. Sorry for the mistake. Yeah, for the one hot encoder also I have to check this. So yes, it is handling the unknown values here. Now if I run it, of course I'll get some error which is like none of indexes in above are in the columns. Oh yeah, okay. So I am getting this error. Okay, so in test GFI, okay, I have already transformed the test data frame, so I have to do from the starting. Okay, now let me just rerun all the, yeah, so now it worked. Okay, now it worked. Sorry for the mistake, because yeah, 255 cell number here. Now if I check my this is here, this is here, and this is complete my I have joined my ordinal encoded columns, one hot encoded columns with my original training data set. Okay, now this is the data set we have. So now let's count for the NaN values. Now we don't have any NaN value, of course. If we still have, because we have already handled it, right? If we still have, we can handle those as well. Like we have just right now we did with the -1, right, for the cabin. What we can do is we can simply replace those -1. So xtrain I'll pass xtrain equals xtrain dot replace -1 with np.nan. Okay, and the same thing I will do for the validation also. So xvalid, and the same thing I will do for the test TF also. So this is how we will get all the NaN values back. Now here you can see in cabin I have 555 44 NaN values. Of course -1 is not a good approach right here, setting -1. And in xvalid we have some NaN values here, and in test here we have some NaN values here. Here you can see name, our NaN values, and ticket in there in cabin. Now what we can simply do is let's count for the NaN here. Of course we don't need the NaN columns here as of now. Let's just use the most frequent strategy here. So it will impute in all the columns, it will work for the it will find the most frequent value in each column and it will impute it with the NaN value. Okay, Now let me now of course it will work for this also. Okay, because it will find the most frequent in all the columns. Like I have passed the complete data frame, so it will work for whole data frame. And now let me pass the columns again. So the columns are extrain.columns because I'm passing the complete data frame, right? Let me do the word wrap here. Same thing I do here. This time no mistake for the fit transform. Here it is valid, x valid, x valid, x valid. Here it is just gf. So test gf, test gf, test gf. Now let's just assign extrain is my this, x valid is this, and test gf is this. Okay. Now let's run it once and check extrain dot height. So this is my extrain. Now let's check for the nan values. If we have extrain dot is none dot sum, we have 0 nan values. I can do the sum here also to check. Same for the x valid, here I have 0. Same for the test here. Okay, so now I don't have any nan value, and all the data is now in numerical format, and now it is kind of ready for the model. Okay, now all the data is in float data type because we have converted into nan minus 1 to nan, right? Of course we can convert it back, but we don't need right now. Let's just forget it. Okay, in x valid also let's check info. Yeah, so that nan column which was earlier created, because it is now it is not created because we have already handled it. Okay, we have already handled it here. Handle unknown ignore total word wrap. Yep. Now let's what should we do now? Okay, now our data set is ready. Now then we have feature engineering. We are not doing any kind of feature engineering today. Let's do it in the next session. Now that then is feature selection. We are not doing any kind of feature selection also. Now let's do the modeling stuff. Now let's create some models. Okay, so 7th I guess. Okay, for the models let's use, this is a binary classification problem, so let's take two models here. One is logistic regression, second is decision tree. Okay, I hope you all are aware with these two models, how these work. Okay, I'm just thinking, yes, 7 it was. Now let's import those models as well. So sklearn dot linear model. In linear model API we have our logistic regression, and in tree we have tree API, we have decision tree. This is a classification problem, so we are using decision tree classifier. Okay, so these are two models which we generally have, like which we are using today. Now let's use them. First let's create LR model, which is logistic regression. So logistic regression, I'm not doing any kind of hyperparameter tuning. Dot fit, and I'll pass x train comma y train. Okay, now I'm getting some warning, convergence warning, total number of iterations, which I can set my iterations also. So in logistic regression, if we check, we have a parameter called okay, penalty total and a lot. We can simply change the maximum iterations. Okay, so no worries about this warning. Our model is created successfully. Okay, it is failed to converge. Basically it is due to some scaling also. So now let's create another model, which is decision tree. So I'll write tree model equals decision tree classifier, and now I'll write tree model dot fit xtrain ytrain. Here you can see both models are created, the data is fitted. Now another part which is evaluation. Here we will use the validation set. How? Let's check. In the evaluation, what we will first do is let's find the validation. Well, like let's predict the data, the survival, the target label on the validation dataset. Okay, so lr valid, lr y valid. Okay, let me say y valid, y underscore lr valid. That is more readable. So here I'll write lr model dot predict. I'll simply pass x valid, and same for the y tree valid, lr model dot predict x valid. I'm doing for both of this. Okay, let's check some samples also. So y lr valid dot head. Okay, this is a numpy array, this is not something like that, so I can simply check something like this, the first 5, not the first 5, let's check for the first 10. So these are the first 10 for the linear logistic regression, then for the decision tree these are the first. So first 10 are same, like you can see. Let's check for 20, so just for the sake of getting some different values. Okay, so here also we have all the same, but of course there might be some differences also. No worries about this. Okay, now the original data which we have is this. Okay, I can, like, this is the original data we have. Okay, now we have to mainly check whether it is how accurate our model is. How we will do is we will evaluate our model based on the validation set. How we will do this? Let's first this is the data. Okay, let me just write head here. Okay, what we will do is let's create a function named accuracy. Of course there are various metrics and all metrics are present in scikit-learn library, but I am not using just for the sake of right now. So in accuracy I'll take the actual values which are y true. Okay, and I'll take another which is y predict or y pred. Okay, so these are the predicted value, these are the actual y true values, and I will check whether they are same or not. Y true equal to y pred. It will give me the false and like false or true, okay, indexes. Then I can simply do the sum here, right? The sum here to check like how many are same. Then I'll divide it by length of like the total. Okay, so length of y true, so it will give me the accuracy. Okay, you might be wondering what this is. So this one is like same as doing this total equals 0. If I say now for I in range len of y true, I'll just simply do if y true I equal to y pred I, then I'll increase count plus equals 1 instead of total. Let me write count here. Okay, now here I got the sum. This is the sum. Okay, let me write it here also. This is the sum. Now I will, for the accuracy, of course accuracy can be in percentage, can be in points, that doesn't matter. I can simply divide by the len of total number of values. Okay, so this is how like the accuracy is being computed. This is same as this. Okay, doesn't matter which one we use. If I run it now to calculate the accuracy, so let's check our logistic regression accuracy, LR accuracy. Here it is accuracy, and in accuracy let's first pass y valid, which are true y values, true y labels, right? Which are actual. These are the actual values we have. Then we will pass the y predictions, which are these. So y LR valid this, okay, or y LR pred also I can say rather than valid, just for the sake of naming. So instead of, yeah, okay. Now same I will do for the tree accuracy. Okay, here I'll pass tree underscore pred, not the valid, pred, and let's run. Okay, I am getting some error. Just key error 0. Okay. My y true is a series. It is not an array. Okay, so I can simply convert it into array also. So y true, or I can simply like, yeah, np dot array and y true. Now if I do this, I'll get my accuracy. So my accuracy for the linear regression, logistic regression is 75%, 76% almost, 75.759. Okay, for the tree model it is 759. Both are same, you can see. This is just a coincidence. Okay, so if you use some better model you will get some different accuracy. So this is just a coincidence. You cannot like say like both are giving me the same value. Okay, so this is how we evaluate our model. So let's suppose if we get, okay, so there is a parameter in decision tree which is called max depth. If I set it to let's say 4. Now if I do the prediction, I'm not sure, I may get the same accuracy again. Yeah, I'm getting the same accuracy again. Okay, no worries. Well, it will increase, it will lead to overfitting if I do this again. Okay, we are getting the same accuracy, doesn't matter. So yes, this is how we do the model evaluation. We check which one has the higher accuracy. So here both have the same accuracy, so let's consider our logistic regression has higher accuracy. So I'll write best model is LR model, okay, which is this. Don't worry, in further sessions I'll show you one way with which we can automate all this stuff, all the model evaluation. Okay, there is a lot of stuff which is after like selecting the useful features. So this is the best model I have. Okay, let's consider this. Now I'll do a test prediction. Test preds equals, what I'll do is my best model dot predict. Okay, here this comes under that part, predicting 9th one. So let me write here predicting. Okay, so here I'll pass, what I'll pass here, I'll simply pass just here, nothing else. So these are all my test predictions. Now to submit it, how to submit it? Let's there is a file named gender summation, right? So let's look into how this file looks. So sample ds equals kd dot read csv and sample ds dot head. We have to submit it in this manner. Okay, so we have to first pass the passenger id, which is the index in the test gf, and then survived. Okay, so here if we see in test gf we have this index passenger id. This is the passenger id, right? So this is same, and then we have to pass the predictions in survived column. How can we do so? We can create a column output or predictions, anything, a data frame mainly. And in this data frame I'll pass a dictionary. What this dictionary, this is the dictionary I am passing. Okay, what this dictionary contains, it will contain two columns. First column is this passenger ID, which is having the index, this gs.index. Then I have this one, survived. Okay, and here in survived I'll pass these predictions, test spreads. Okay, and now if I simply run this and see my output, see this is in the same format as this is. Okay, now what I have to do is there's just one last step, um, which is we have to create a submission file. How can we do so? Output dot to underscore csv dot slash is just a reference. I can directly write submission dot csv, doesn't matter. And I also have to set index equals false, which is because if I don't set, it will consider this also as a column. Okay, I'm just ignoring the index here, so that's why I have to set this. Now I have run this is ran. Okay, now my submission.csv is created here. If I open it now, yeah, I have reloaded it. Here you can see this is my submission.csv. I can directly submit it from here also. So now those who have MLP project, this is very important, you can directly submit it from here also. Okay, after importing the data the way I did, or there is another step, which is first, for that, like, we have to save this version. So this here I can write data pre-processing and basic model. So this is the first version which I have created, and let's click on save. Now let's click on open logs in viewer. Now this is running my code. Okay, this is creating a final notebook. This is basically saving my code with whatever I have done here. Okay, now here you can see everything is running. So it will take about 1 minute or so. So it is running very fast. Now just only, yeah, now it is converting it to the actual format which can be displayed here in the node. Here you can see notebook actively running, and in the output now we don't have. Okay, now we got the output also. So in the notebook section, here you can see this is all the code which we did today, right? So this is the complete code, and in the input we can see the input files which we have inputted. These are these files. This is the input. Okay, and the output we have submission.csv. Same way in the output section we have submission.csv. Now there are three basically ways to submit. First is directly from here, like while writing the code. Okay, after having the submission.csv. And the second is from here, like clicking on the submit button or clicking on this submit to competition. Then there is another way, which is this, like when you have participated in the competition, when you have joined the competition, click on submit prediction and click on notebook, and here I have selected, this is my notebook, right, and I have only one version, so I can select this, and the output file is also selected here. Let me zoom out. Okay, and I can submit it from there, and I can also write any sample description. So there are three ways. This is the third way, this is the second way. Okay, either from here or here, and this is the first way. So let's do it from the third way itself, because in our MLP project competition we will only working with one notebook and various versions we will be having. Okay, so make sure you name your versions accordingly what you have done. So today we have done data processing, that's why I have named it as data pre-processing and basic model. Now if I run submit it, here you can see it is getting submitted. So this is now submitted. These are my old submissions. Okay, you can ignore them. So this is the submission. So I got a score of 0.76. So this is the accuracy which I got on my test data set. Okay, how can we see it? If we go to leaderboard, and this is how you will get an overview. Okay, if you click on jump to your leaderboard position, so this is my position. My position is 13,056. Of course, this is a playground competition, so there are so many participants. Okay, same way you have to do for the crime cast competition, and here you can select two best submissions also. Okay, so yes, this is all about today's session. I hope you all have you all got clarity about how to do the data pre-processing. Now I will share this notebook with you all in the recording. Okay, in the YouTube video which you can access from here. This is my channel. I'll upload the recording here and you can access it from this. Okay, and the notebook also I will upload. And now in next session we will mainly look into this fifth step first, feature engineering, and sixth one, and also we will do the modeling and we will create a complete pipeline. Okay, so that will be very interesting. So yes, let's meet in the next session. I hope today's session is worthy for you. I have recorded this once again because of electricity cut off in my area. My old recording was lost, so I hope you find it useful, and thank you guys for watching my session. Let's see you in next session. Bye.